Hello everyone, welcome to the second week of CIV5305. This week lecture um, will be allocated to some of the topics covered in chapter 3 of the textbook on data and space. So in this lecture, we will discuss some of the issues in data collection and their representation for use in travel demand modeling. You will be provided with a brief introduction to statistical sampling theory. We will discuss the nature and importance of errors, which can arise both during model estimation and prediction. We will also cover various types of surveys that are used in travel demand modeling. And we will also discuss some of the issues in collection of stated preference data and longitudinal or panel data. So let's start with basic sampling theory. We use a lot of data in travel demand modeling. The data we use in modeling travel demand usually consists of a sample of observations taken from a population. It is usually not very economically or sometimes technically feasible to observe the entire population. Well, this is changing these days with the increasing availability of data from mobile phones. In some certain areas that have high penetration of mobile phones, you can actually observe or collect data from almost the entire population. Well, however, we still rely on a lot of sample data. There's this notion of sample design in sampling theory, which aims to ensure that the data that is collected provide the greatest amount of useful information about the population, or in other words, being sufficiently representative of the population. There are some main difficulties in sampling. The first issue is ensuring a representative sample. If your sample does not agree with the characteristics of the entire population, for example, if your sample have a different population demography than your population, or it covers a different geographical area from the entire population, it is very likely that your sample is not representative of the population. There's another difficulty in sampling, which is how to extract valid conclusions from a representative sample. After you collect a representative sample, how can you make sure you extract valid conclusions from it? There it comes different sampling methods. We have random sampling, which is the simplest way of sampling. We have a stratified random sampling, and we have choice-based sampling. In a simple random sampling, obviously, as it says, the selection of sample is totally random. But what is the problem with this method? It may require a large sample size to ensure we have sufficient data. A stratified random sampling is a little bit better than totally random sampling. In a stratified random sampling, we basically break the population into different strata or different categories, and then we try inside each category, we try to collect random sample from each category. So a priori information is used to subdivide the population into homogeneous strata or layers or groups, and then simple random sampling is conducted inside each group or layer. The other way of sampling is called choice-based sampling. Instead of stratifying population based on some demographic or geographic or location, in travel demand modeling context, we group the population based on a choice. For example, in a mode choice analysis, if you want to collect some data, you may subgroup the population into groups associated with their mode choice. For example, we can have a group of people using private vehicle. You can have a group of people using public transport, or you can have a group of cyclists within your population. And then within these groups that are subdivided based on their choice of mode, you can conduct a random sample. That is called choice-based sampling. When it comes to sampling, it is important to differentiate between error and bias. Error is due to random effects, while bias is due to mistakes. Error is simply due to the fact that we're dealing with a sample and not the entire population. as expected error will always be there when you do sampling. Sampling error does not affect the expected value of the means of the estimated parameters. It only affects the variability around those parameters. However, bias is caused by mistakes made either when defining the population or when selecting the sampling method. Or there might be mistakes in data collection techniques, or any human-made mistakes during other process of your data collection. Sampling bias, unlike the error, can affect the mean value of the estimated parameter in addition to the variability around them. And good thing about bias is it can be avoided. In sampling, it is very important to determine the right sample size. As a matter of fact, specifying the right sample size is a problem of trade-offs. If you collect a very large sample size, it may imply a data collection and analysis process that is very expensive, given the objective of your study or the accuracy you need. However, if you also collect very small sample, it may imply that your results are subject to unacceptable high degree of variability, which may not be appropriate for your study. I think this is a good time now to have a look at activity 2.1 that is provided on Moodle. Let's go over the activity together. In this activity, we will go over the example 3.1 of the textbook. Consider a certain area whose population may be classified in groups according to automobile ownership, with or without a car, and household size, up to 4 members in the household and more than 4 residents in the household. Now let us assume that M observations are required by each cell or group in order to guarantee a 95% confidence level in the estimation of, let's say, trip rates. Now assume that the population can also be considered to have approximately the following distribution. So we can group the entire population into 4 classes or 4 cells. One cell represents ownership of a car, having a car, with car, and 4 or less members in the household, which is 9% of the population. Another group is having a car and having more than 4 members in the household, with 16% of the population. The other group is having no car and having 4 or less members in the household. That constitute 25% of the population. And the last group is without a car and having more than 4 members in the household, which is 50% of the population. Now the question is, how can we collect a sample from this population that guarantees a 95% confidence level in the estimation of whatever we want to estimate, let's say trip rates in this case? To guarantee that 95% confidence level, the example assumes that we need M observations from each group here. So the first way of achieving this is to make sure we have M observations from each cell randomly. So what we need to do is we need to have a look at the smallest group, which is the 9% of population group, and make sure we have M observations from that group specifically. If we make sure we have M observations from that group, then we will also be sure that in the rest of the groups that are larger, we will have more than M. So the sample size would be M divided by 9%, which gives you 11.1 M. There's another method to collect a sample from this population, and it is a stratified way of collecting the sample. What you can do is you can undertake a preliminary random survey of this entire 11.1 M households, but instead of collecting the entire data that you want, you can only collect a small survey. You can only ask them about their cell or group membership. You can only ask them about whether they have a car or how many household members they have in their household. So this is relatively a low-cost survey. So from this low-cost survey, we can obtain the addresses of M households even in the smallest group. Therefore, as only M observations are needed from each group, it is then sufficient to randomly select a stratified sample of 3M households from other groups, plus M observations from the smallest group, so total 4M observations. Now compare this 4M versus the 11.1 M observations we collected with the previous method. Obviously, this is a much smaller sample, but it is as representative as the first method. However, you need to take into account the cost of the preliminary survey versus conducting the entire survey for 11.1 M observations. Next, in this week's lecture, we will go over some probabilistic or mathematical conceptualization of the sampling problem, or to basically formulate the sampling problem as a probabilistic problem. So we will assume that the final objective of taking a sample is to calibrate a choice model for the entire population. And in this formulation, P represents the entire population and F represents sample characteristics. So we will also define I and X, where I represents the observed choice of an individual. For example, in a mode choice context, I could be taking a bus, driving a private vehicle, or walking or cycling. And X is a vector of characteristics, representing attributes of individual or attributes of the choice set. There are a few other assumptions in probabilistic formulation of sampling problem. And that is the underlying choice process in the population can be represented by a joint distribution of I and X, which is represented as probability of I and X conditional on theta. Theta is the parameters in the model. And also we assume that the probability of choosing alternative I, for example, different modes in a mode choice context among a set of options, with attributes X can be represented as probability of I conditional on X and theta. So the first one is a joint distribution of I and X given some parameters of theta. And the second one is the probability of choosing alternative I with attributes X and model parameters theta. So how can we formulate a random sample? In a random sample, we must make sure that the distribution, the joint distribution of I and X in the sample is identical to the joint distribution of I and X in the entire population. Therefore, on the left-hand side of the equation, you have the joint distribution of the sample. Remember, sample was represented by F. And on the right-hand side, you have the joint distribution of I and X in the entire population. We have it represented by P. So joint distribution of I and X in the sample is equal to the joint distribution of I and X in the entire population. And that's the definition of random sample. The stratified sampling is a little bit more complex. The sampling process is not entirely random anymore. Rather, it can be defined as a function fx. Therefore, we can express that the joint distribution of I and X is a sample as dependent on fx, which was a function representing the sampling process multiplied by the probability of I conditional on X. We can also rewrite this equation in a way to show that a random sample is just a special case of a stratified sample. If you replace fx, which was the sampling process function, by px, px basically means a totally random sample, the probability of choosing x, multiplied by the probability of I conditional on x and theta, you can get the same formulation for a random sample. So a random sample is just a special case of a stratified sample. Before going over the formulation of choice-based sample, let's refresh our knowledge of probabilistic. If you remember from your probably the last probability and statistics class you've had, We have a theorem called Bayesian theorem or Bayes theorem, where it states that probability of A conditional on B is equal to probability of B conditional on A multiplied by probability of A over probability of B. If you feel a little bit uncomfortable with these concepts of probabilistic and statistics, I would encourage you to have a look at chapter 2 of the textbook. Go over it and refresh your mathematics and probabilistic knowledge. So in a choice-based sample, again, it is very similar to the stratified sample. However, the sampling process is not anymore represented by fx, which is a function of the attributes. Rather, it is a function of the choices. Rather, remember, I was representing the observed choice. It's a choice-based sample. So instead of fx in a stratified sample, we replace this with fi, which is the sampling procedure in this case. Therefore, we can express the formulation of a choice-based sample as the joint distribution of I and x in the sample is equal to the function fi, which is the sampling procedure based on the choice of alternative I, multiplied by probability of x conditional on I and theta. If we apply the Bayesian theorem to this formulation, we can rewrite this equation as this equation on the bottom, where we have the probability of x conditional on I is equal to the probability of I conditional on x multiplied by px over pi conditional on theta. If we rewrite that part of pi conditional on theta in a different way, in a discrete form, as a summation of probabilities, we can then rewrite the final expression of the joint probability of I and x for a choice-based sample as it is shown here, which is pretty ugly, if, as some people say, or more precisely, it's very complex, as we see it here. To better understand what I'm talking about here, if you don't really understand these probabilities, let's have a look at activity 2.2, which deals with some of these concepts in a more clear way. So let's open activity 2.2 and let's go over it together. So in activity 2.2, we will go over the example 3.2 in the textbook from chapter 3. Assume that for the purpose of a transport study, the population of an area is classified according to 2 income categories, and there are only 2 means of transport available, being car and bus, for the journey to work. Let us assume that the population distribution is as given in this table, where we have 4 categories or 4 cells, bus user and car user, low income and high income, where we have 45% in this category, 20% in low income and car, 15% in high income and bus, and 20% in high income and car, and the total would be 100%. So if we collect a random sample, a totally random sample, we expect that the same population distribution will exist in the sample. The exact same distribution we'll see in the random sample. However, in a stratified sample, we expect to see a different distribution. Now assume a sample with 75% low income and 25% high income, which is different from the original proportions in the population, which was 65% low income and 35% high income. We have 75% low income in the sample and 25% high income in the sample. So from the previous table, we can calculate the probability of a low-income traveler using a bus, which basically can be represented as probability of bus conditional on being low income, which can be expressed as probability of being low income and using a bus over the probability of being low income. So probability of being low income and using a bus is 45%. Probability of being low income can be represented as probability of being a low income and using a bus plus probability of low income and using a car, which is basically this 65% here. So 45% over 65%, we get 0.692. Now in our stratified sample, we have 75% low income. Therefore, the probability of finding a bus user with low income would be 75% multiplied by this number, which was the probability of bus conditional on low income. Therefore, the probability of a bus user with low income would be 0.519. You can continue this calculation for every other category or every other cell to get the new distribution of categories in your stratified sample. And then you can compare this with the original table and you can see how the numbers you get are different. So in fact, if you want to get something that is totally representative of the population, this stratified sampling will give you a different distribution. In a choice-based sample, we do it slightly differently. Assume in a choice-based sample that we take a sample of 75% bus user and 25% car user. In the original table, we had 60% bus user and 40% car user. Here we have 75% bus user and 25% car user. So it's a choice-based sample. Therefore, the probability of a bus user having low income can be calculated as the probability of low income conditional on bus is equal to the probability of low income and using a bus over the probability of using bus. So the probability of being low income and using a bus from the original table was 45%, while the probability of using bus, which can be represented as probability of low income and bus plus probability of high income and bus, which gives you the total probability of using a bus, which was 60%. The bus user is 60%. So the probability of low income conditional on bus would be 45% divided by 60%, give you 0.75. Now in our sample, we had 75% 75% bus users. Therefore, the probability of finding a low-income traveler using bus would be 75% bus users multiplied by this probability, which was also 75%, gives you 0.563. Again, similar to the previous case, if you continue this calculation for every category in your table, you get the new distribution in your choice-based sample. And again, if you compare this value to the distribution in the stratified sample and to the distribution of the original population, you see how different they are and how different sampling method can give you a different distribution. In the second part of this activity, we'll go over a very interesting property of random samples and stratified samples. So it is relatively easy to get the probability of someone being high income selecting a car. This can be calculated by taking the probability of the traveler being high income and using a car divided by the probability of being high income. So if we calculate this probability for the original population, which is basically the same as the simple random sample, we'll get 20%, which is the probability of having high income and using a car if you look at the original table, and divided by probability of being high income, you get 20% over 35%, and you get 572. Interestingly, if you calculate the same value for the stratified sample using the values you have in the table associated with the stratified sample, you get the same number. This is not a coincidence. In fact, this is one of the very interesting and important properties of a stratified sample that was shown by a seminal work of Lerman in 1976. It is also important to note that this property doesn't hold for choice-based samples. If you calculate the same value, which was the probability of being high income and selecting a car, over the probability of being high income using the values in the choice-based table, you get a different probability. In fact, when you want to calculate or estimate a mode choice model, it is very important to take this into account, that if you have a stratified sample, you automatically, as the property of this stratified sampling, you get similar properties. But if you use a choice-based sample, you get different probabilities, which might be problematic. However, The same person, Lerman, also proposed a method to how to use data from choice-based sample to avoid this bias in modeling. You can go over the rest of the activity yourself, but it is a little bit beyond what I'm going to cover in this unit. But it is nice to bear that in mind, bear this property in mind when we go over the discrete choice modeling materials in a few weeks from now. In the last activity of this week, we will go over example 3.3 of the textbook, which is about how to estimate subpopulation fraction from a small survey and some limited information. So assume the following information is available. We know the average income of the population, which is $33,600 a year. We know that the average car ownership of the entire population is 0.44 cars per household. Now we conduct a small survey, a small unmode survey, to get the following information. So we now, from the survey data, we know that car users have an average income of $78,000 a year and a car ownership rate of 1.15. Similarly, from the survey, bus users have an average income of $14,000 and a car ownership of 0.05. And metro users have an average income of $38,000 and car ownership rate of 0.85. Now, we are interested to get the subpopulation fractions. We want to know how many people have car, how many people have bus, and how many people use bus, and how many people use metro. So F1 relates to car users, F2 relates to bus users, and F3 relates to metro users. We can set up a system of simultaneous equations now. As we know the average income of the population and we know the average income of each mode user, we can set up the first equation where the fraction of car users multiplied by their average income plus the fraction of bus users multiplied by their average income plus the fraction of metro users multiplied by the average income must be equal to the average income of the entire population. The second equation is very similar but with the car ownership rate. The fraction of car users multiplied by their car ownership rate plus the fraction of bus users multiplied by their car ownership rate plus the fraction of metro users multiplied by their car ownership rate must be equal to the average car ownership of the entire population. And obviously we know that the sum of the fraction of the subpopulations must be equal to 1. Now if we solve this system of simultaneous equations, we get the individual percentages, the subpopulation fractions actually, which tells us that 24% are car users, 60% are bus users, and 15% are metro users. And now if you multiply this by the entire population, let's assume it's about 180,000 inhabitants, there would approximately be 44,000 car users, 108,000 bus users, and 27,000 metro users.